and welcome back to the second video in the 12th and last lecture of Covidenomics. And in this video we're going to take a bit of a detour just to remind ourselves of Bayes' rule, or sometimes called Bayes' theorem or Bayes' law. It's all the same thing. So I'm going to call it Bayes' rule because that's the name I tend to call it. Wikipedia, where I've got this from, is calling it Bayes' theorem. And they chuck two S's in there, which I don't do either. Bayes' rule, or Bayes' theorem, basically says that you can work out the conditional probability of event A occurring given event B has occurred from the following formula. It's the probability that B occurs given A has occurred times the probability of A all over the probability of B. And you've got the relevant definitions down here. That's probably as clear as mud to you. To understand this better, I'm going to run through again a simple example. So suppose that we have two events that are mutually exclusive. In other words, either one can happen or the other can happen. They can't both happen at the same time. And they cover all the possibilities. So one of these two events will occur. Obviously, you can extend this to 3 or 4 or 5 or 6 or however many events you want. We'll keep it at 2 to keep it simple. So given that I'm recording this on Sunday after the AFL Grand Final for 2020, let's look at that as our event. And there were two possibilities of what happened last night. Either Richmond won the Grand Final or Geelong won the Grand Final. For any of you who don't follow Australian football, they're the two teams were playing in the 2020 Grand Final. So that's the only two possible events, and they cover all possibilities, and they are mutually exclusive. You cannot have a draw in the AFL Grand Final. There's various rules to make sure that you keep playing until somebody wins. Now, let's say that I don't know who actually won the Grand Final last night, but I go for a walk, and I take a walk down Bridge Road, which is one of the main streets in the suburb of Richmond in Melbourne. And there's two possibilities there that are also mutually exclusive and cover all possibilities. I either see a Richmond football flag during my walk in Bridge Road, or I don't see a Richmond football flag on my walk in Bridge Road. Now, suppose I get home, I still haven't listened to the news, I don't know who actually won the Grand Final, but my wife asked me, did Richmond win yesterday or did Geelong win? How should I answer her? Well, the answer is I need to use Bayes' rule, because I've now got some information. I may or may not have seen a flag. I have my prior probabilities that either Richmond or Geelong won, but I have more information from my walk, and I want to put all of that together to give my wife the best possible answer. So while I didn't watch the Grand Final, I did look up the bookmakers' odds just before the Grand Final began. And the bookmakers had the chance of Richmond winning, probability of the event that Richmond wins, which I'll call R, as being 60%, and the probability that Geelong wins was given by 40% by those bookmakers. And now let's suppose that if Richmond had won, then look, it's pretty likely I'm going to see a Richmond Footy Club flag on Bridge Road. So let's say there's a 90% chance that I'll see a flag if Richmond won the Grand Final. But even if they lost the Grand Final, Richmond supporters are loyal. They'll still be hanging the flags out on Bridge Road. So look, there's still a 70% chance that I'll see a Richmond football flag on Bridge Road, even if Geelong rather than Richmond won. Now, to answer my wife's question, who won the Grand Final, I'm going to use a slightly different version of Bayes' rule. So here I've written the probability of A given B is the probability of A intersecting with B and divided by the probability of B. Sorry for the writing. I suddenly found out that my mathematical editor doesn't have the intersection sign available to me. Sorry. So you get my bad writing instead. How does this relate back to that Wikipedia formula I showed you earlier? Well, notice that I could also write the probability of B given A is the probability of B intersecting with A over the probability A. Remember, the probability of B intersecting with A is the same as the probability of A intersecting with B. So I can simply rewrite this as by taking the probability of A over to the left-hand side, as probability of B intersecting A, which is probability A intersecting B, same thing, is the probability of B given A times probability of A. And if you simply substitute that back up here, you get the Wikipedia formula, which is just probability A given B is equal to probability of B given A times probability of A, that stuff down here, all divided by probability of B. So that relates the two formula back together. So let's go back to our original problem. I get home, I finish my walk. During my walk, I did in fact see a Richmond Football Club flag in Bridge Road. And my wife asked me, who won the grand final? Did Richmond win? I can't say definitively, but I can give her the probability that Richmond won. The probability of Richmond winning, given that I've seen a flag. We know by Bayes' rule that that's equal to either the probability of R intersecting with F over probability F, or the probability of F given R times the probability of R over the probability of F. They're the same thing. That's what we just showed. Now, this is good, because I have some of this stuff. I have, first off, got the probability of F given R. That's 0.9. I've got the probability of R. That's 0.6. But I don't have the probability of F. So I need to use another little trick just to fill in this gap. And this other little trick is to note that the probability of seeing a flag is equal to the probability of seeing a flag intersecting with Richmond having won the grand final, plus the probability of seeing a flag intersecting with not Richmond winning the grand final. Now, because the only alternative here is for Geelong to have won, it's a probability of seeing a flag intersecting with Geelong winning. R and G are mutually exclusive and cover all alternatives, so simply adding up these two intersections gives us the total probability of seeing a flag. But we know what each of these is. We know that this first probability is simply equal to the probability of seeing a flag given Richmond won times the probability of Richmond won, and we've got all that information. And this second probability over here, well, it's simply equal to the probability of F given G times the probability of G, which we worked out before. Again, we've got all this information. Those of you who are paying attention will notice I've now switched to using the appropriate club colours. So we can now work out this probability of seeing a flag. It's the probability of F intersecting with R, which is simply the probability of a flag given R times the probability of R, flag given R times the probability of R, plus probability of flag intersecting with not R or G in this situation, which is going to be the probability of a flag given G, 0.7, times the probability of G, 0.4. So the probability of seeing a flag on my walk down Bridge Road the day after the grand final, if I didn't know the result, the probability would be 0.82. And I can now substitute that back in and get the final result. So I've now got the probability of F given R, 0.9, the probability of R, 0.6, and the probability of F, 0.82. Substituting them in, and the probability that Richmond won the grand final, given that I saw a flag on Bridge Road, is 0.9 times 0.6 divided by 0.82, or 0.66, or about 2/3. So after my Sunday morning walk, when my wife asked me who won the grand final, I'll be able to say, with about 2/3 probability, Richmond did, because I saw a flag on Bridge Road. At which point my wife will sigh and get out her phone and just Google the answer, because, yeah, Richmond did win quite convincingly, but who cares, because Carlton wasn't in the grand final. So, hopefully you found that detour into Bayes' rule, or Bayes' theorem, or Bayes' law useful, at least as a reminder. AFL grand final's gone, who cares? Melbourne Storm is, however, in the NRL, or the Rugby League Grand Final tonight, against some unknown Sydney team. So hopefully I'll be smiling with at least one team of mine winning over the weekend. Talk to you in the next video.